So up to here, I was showing you how actually we can solve the transient problem for RL or RC if they are connected to the DC sources and they are charging, or they are disconnected from sourcing and they are discharging. And what we went through up to this point is that how you can do it actually through the writing the equation and solving the solution and get the solution for that. But there is a shortcut to do that when you learn that, and it's that we know that the again, this solution, this shortcut is only working if there is no sources or there is the DC sources that we are going to use that. So this solution is like that. We know that the solution for the transient either is going to be the voltage or it's going to be the current over time is equal to the final value so the final value of either of these two, and I will explain them, what does it mean by them, plus the initial value minus final value times e to the power of negative t over tau. So our solution is going to be look like this. And now let's see what I mean with each of these terms. So the final value, what I mean by that is the condition that here is basically when the t is going toward infinity. So if we leave the circuit for long time, whatever is happening there, that's going to be final. So if we are looking for the I, if we just leave the circuit for a long time, whatever value we have for the I is our final value. Here the initial value is also that is what happened at the t is 0, when the time is 0, and again the final value is when the t is going to infinity. So we'll leave it to be there for a long time. If you remember from the solution we have up to this point, this part is actually the K1 when we write the solution, and then this part is the K2 in when we write the solution in when we have the solution we're using them. And generally is like that. So the K1 the K1 is the steady state condition. So this when we say that let the t go through the infinity, it is the is as a result of steady state condition. So this is as a result of a steady state condition. Basically, let's put it well, let's put it the other way, so it's probably better. So this shows the I would say this K1 shows the steady state condition, as a result of source. Source. So we can consider that as a steady state condition, and then this part, this second part, the second term basically is the transient condition, or it shows the transient condition as a result is as a result of any initial uh, condition. So basically what as I said, our response is going to look like this. It's final value plus uh, so final value plus the initial value minus value e to the power of t divided by tau. So that final value is when we leave the when we leave the circuit to be there for a long time. Basically, it gets to the steady state condition, and that's the K1. And then this part is the initial the initial value is when the transient wants to happen. Either we open the key or close the key right at the moment the transient starts. That's the condition. And the difference between these two is basically the K2 that we have it in the previous solution, and this is going to be e to the negative t to the power of tau. So in other words, I can write it here. So I will write. So I can write the Vt or um, so yeah, the Vt or It is equal to K1 plus K2 e to the negative t over tau. And the K1 is the final value as here, and the K2 is the difference of these two. Now, and we know that because the K1 is a steady state condition, if there is no source in the system, we know that eventually it's going to become zero. So if there is no source in the system, the K1 becomes zero. So we know that. So the couple points. So if there is no source, then eventually the K1 would be zero. And for also the RC, we know that the tau is equal to RC, and for RL circuit, the tau would be L over R. So consider this condition, and I will show you how we can use that for a simple solution. Okay, just make sure that these two, I will write these two are for DC or no source. So we cannot use this method for the AC transient. So it's only should be either we have the DC source is for DC source or for no source. So for DC source or no source. That's how we are gonna have them. Okay, let's look at how we can use this method to find a solution for the transient condition. So assume that we have a circuit like that. So it's going to be connected to the 100 volt battery, and it's connected to like that, error resistance, and then another resistance, and then it goes through inductor, and goes back here, and then we have a key up here, have the key up here like that, and something like that. And for t less than 0, I would say for t less than 0, key is closed. So for t less than 0, the t is closed. So it's gonna be key is closed. And then at t is 0, we open the key. So this is the condition we have, and now we want to find for such condition we want to find the transient. So it's 100 volt, is 100 O, this is 100 O, and this is 1 henries, and then we have the current goes here through that inductor is going to be I over T. So I want to see what happens if we open the key at time is when the time is becomes 0. So we know that solution that the solution that we just talked about is that and we are here look for the I, and you can do it also for the um, uh, V as well. So for the I, we know that the Vt is going to be the final, so the final value um, plus the initial value minus final value e to the power of negative t over tau. So so basically what we are going to have here, we're going to say is that the Vt is equal to final value is the or here we are doing the it first. So the it, so the it is equal to final value is the I that when the t is go to the infinity, plus for the again the initial value when the t is, or the I when the t is 0, minus final value is when the t again goes toward the infinity, and then times e to the power of negative t. And we have here look at here when look at when I open that key, when I open that key at t larger than 0, so I have r, so basically there are two r's one after another, so I can combine them and have one equivalent r and l. So I have a rl, so because I have the rl, the tau is going to be equal to so I'm going to write it like that, so negative t and the tau, and I would so the tau is going to be L over R. So I'm going to use these terms to see how we can get. So First of all, let's see what's happening if the t is going to be at the initial condition. At the very initial condition is when I open that key, and the key is going to become open. So that's the initial condition. At t0 is going to be like that. So it would be open at t0. So let's see what's happening at t0. At t0, we know that it's going to be for all the t0. So initial condition, it was like that. It was closed for a very long time, and we open it at t0. So if we want to see what's the condition, is that this is what we are going to have for the t is 0. Basically, the condition of that is, I'll put the negative here. It's just before we open the key. Right before we open the key is our initial condition. If we want to see what's happening here, we'll have this, and then we have that key up there, and then we have this one, and then we have this, and again, let me do it because it's up. Well, let me draw that first. So what happened here is that as soon, because the key is closed for a long time, basically nothing goes through this R here. So it would be like that. So it would be, we don't have anything connected there because all the current is gonna short circuit around that. And then we have this 100 ohm here, and then here also, because it was closed for a long time, the inductor was fully charged, and because it's fully charged, it's gonna behave like a short circuit, like a single wire. So this is what we have at the initial condition. Because the key was closed for a long time, all the current goes through the top leg, the top wire here, then go through the resistance, and then this inductor doesn't do anything and goes back. So for this condition, if I want to consider that, so for the I at t is 0, which is the initial condition, we look for that. We have the 100 volt here and the 100 ohm here. So if I write the ohm law, so let me write the ohm law. Just V is equal to IR, and then I can go ahead, and I know the V is 100, and the I as is the one at the initial condition, and the R is also 100. So the I at T0 is going to be 1 amp. Now we want to see what's happening if the T goes toward infinity. So if the T goes to an infinity, means that we open the key and then just let it to be sit there for a long time. So if we open the key, so the battery is going to be there, and then we have this is the open key right here, and then we have that the first resistance, and then we have the second resistance, and then we have the inductor. Again, if we let the key be open for a very long time, the inductor is going to behave like an open wire. It's going to be behave like a wire. So again, we are going to have 100 ohm here, 100 ohm here, and then the same thing I have done here. So I'm going to say that V is equal IR, and this time again the voltage is 100, the I is as T goes toward the infinity, and the R is the R equivalent, which is, because these two are in series, we just add them together. So again, it's going to be 100 is equal to I T goes toward infinity times 100 plus 100, which this one is equivalent resistance. and therefore if I just do that, so I, when the t is going toward infinity, it becomes uh, 0.5 amp. So uh, this is what I have here. So I have the I goes here and I goes to infinity, so I just need to go ahead and substitute them in this solution that I have. So if I go ahead and say the solution I have was IT was for I that t is uh, going going to the infinity plus for the initial condition t sorry I for t is 0 minus I when the t is going toward infinity, and then e to the negative t over tau. So if I go and substitute there, so I know that the it when the I when the t going toward the infinity, we know that's going to be 0.5. So we'll just replace that with the 0.5. Then plus again the I at the initial condition is going to be 1 amp. So we just put it as 1 minus again the growth phase got 0.5 e to the negative t over tau. And we know that it's the RL systems, because I said if you look at it, after I open the key and leave it to stay for a long time, all I'm gonna have is the two resistance, which I can combine them, and then one inductor. So it's gonna be the RL, because the RL, we know in the RL the tau is gonna be L divided by R, and in this case it's gonna be the uh, equivalent R. So the L is, I think the L is 1 Henry, and the equivalent R is 100 plus 100. So the R is going to be 1 over 200, and if I go ahead and substitute there in equation, so I'm going to get IT, it's going to be 0.5 plus 1 minus 0.5 e to the negative, so I can put it here, t divided by 1 over 200, which eventually I can write simplified. It's going to be 0.5 plus 0.5 e to the power of negative 200 t. If I have write everything correctly, it should be something, it should comes out as this that we have. And the same way we can do it also, if you want to, we can do it with for the voltage as well.